Okay. Can you see my screen?
Yes, we can see your screen, doctor.
Okay, wonderful. Yeah, it's really a delight to be here, with you all, and I'm always very grateful for the opportunity to participate and to teach this course in the boot camp. Since Dr. Bayo Adekombi invited me to be a part of this community, it's been about 5 years, and I've been back every year teaching this, and it's always been a real honor, especially when there's an opportunity to be back home in Nigeria, eating inya, egusi, and amala, and so on and so forth. We didn't have that opportunity this time, but hopefully next year we'll be able to do that again. You all it's a hybrid, right? You have half the team, half of you guys are at Covenant University and some are online. Okay. All right, wonderful. So you guys saw about my background. I'm a physician. I do practice medicine, one morning every 2 weeks thereabouts. But for the most part, mostly in software and data science. And we have a company called Retina AI Health. We're a small startup, but in the medical device space, startups typically it takes you have been in the game for 10 years and still be a startup. So we're a 5-year-old, so we're still fairly young, relatively speaking. And what we're doing is we're building systems using deep learning that can automatically detect diabetic retinopathy and other systemic diseases just using pictures of the retina and using cloud, based systems. So really, deep learning is really my day job, if you will. In this course, we're going to be talking about some of the fundamentals, right? Because I know everybody in the course, you guys have excelled at the 10-week curriculum, and you've excelled at the Kaggle competitions, and you've got your hands on Python. You know how to code. You know what neural networks are, how they work. We're hoping to add some value to you in this short course, this short 1 hour that we have together, by looking at under the hood, what's going on, what exactly is the nuts and bolts of these neural networks. So a little bit about the example of what we do at Retina AI is basically, you have a camera in an office, somebody takes a picture of the back of somebody's eye, somebody's retina, and that goes into the cloud and and then gives a diagnosis. And that basically is how is the role of a doctor for that task. And what's even interesting is that the AI is actually more accurate than human physicians at this particular task. So that's very interesting. Example of a real world problem that utilizes deep learning. But what exactly is this deep learning? So I set out on a quest to find out myself, because it's sort of a vague term that we apply to so many different things, right? And let me see if I can see the chat comments. I'm just going to keep going, but I want to know if there are any questions, or perhaps we'll take them at the end. So I set out to, because I would have liked to also ask some questions, but I'm not sure that I'll have that opportunity given the current format. If I'm wrong about that, please let me know. So I Googled this, and I've found a bunch of pictures, right? And you can already start to see this pattern that most things seem to have this notion of these sort of weaver beam type looking structures. We know what these are, of course. And then I said, okay, why not? Let's go for even a bigger search. And so many different types, so many different patterns, so many different architectures, some even looking like the human brain, etc. And so that sort of starts to give you some idea about what deep learning is, right? So clearly there's something deep about this. And what exactly does that mean? Is it like 2 layers? Some of these have 4, some of these have, looks like they have up to 100. If you look at some down here, some of these are like taper down and then go back up. But what is fundamental about, so clearly the depth is a variable term. Is it 2? Is it 10? Is it 100? Is it 1,000? Is it 1,000,000,000,000? We're starting to see really, really large architectures these days. And what is the learning part of that? Well, ultimately, I surmised that what deep learning is really learning using deep neural networks. And the deep part of it is very relative, and it's going to continue to increasingly be relative, because 10 years from now, who knows what, trillions of depth of networks would be feasible with the compute power that's available. Things that we thought were deep 5 years ago now are not really thought to be that way, right? 16-layer networks were thought to be deep neural networks. Some of the original benchmark ones in the early days meaning like 2012, where the visual recognition challenge started to be begun to be won by neural networks. Things were not that deep. We're not looking at the scale of what we're seeing today. So it's the neural network that matters. It's the neural network that's not going away, right? And it's the neural network that really we need to understand. And once we understand what a neural network is, we kind of understand something fundamental about every AI system out there, about every architecture out there, and probably about every architecture that will be relevant within now and the next 100 years. So we can't underestimate the importance of understanding neural networks. And just as an example, things that look so different from each other, when you lift the hood up, they're all neural nets. Does anybody know what this is? Anybody recognize this at first glance? Let me see if I can interact, which would really be my preference. Maybe I can't, but this is. Let me see. Is it possible for me to? You guys don't have. You're not mic'd, or Okay, good. So either way, I'm sure some of you recognize this. This is a transformer architecture, which really is the basis for all large language models. Large language models have gotten a lot of attention lately, right? Especially with ChatGPT and how they made that available to the general public. And I think it got up to 1 million users within a few days. I don't know exactly what those numbers are, but some kind of record was broken. And it really sort of put AI in another phase of its maturity in terms of its acceptance and its awareness. And people started to realize that, this might not just be hype. So lots of large language models are out there. And they're all based on transformer architectures, everything from BERT to ChatGPT, GPT-4. There's probably over 100 large language models now. All of them, under the hood, is simply a neural network. Another very interesting area, we could go on and on, self-driving cars, autonomous driving, right? Autonomous driving vehicles, however, futuristic or fancy they might seem like, inside of that software that's running this thing is just neural networks. And it's all about training data. It's all about engineering and parameterization, et cetera. And so the fundamentals of how all these different systems work, whatever it is that you're interested in, whether it's healthcare, whether it's autonomous driving, whether it's cities, whether it's agriculture, whether it's fintech, prospecting, whatever the case might be, understanding a neural network will certainly add value to you. And that's what this 1 hour lecture is about. So what is a neural network? Now that we know that it's so fundamentally important, neural network is a basic looking one, right? But it has everything that neural network would have. It has an input layer, and then it has a layer that's not the final layer. Sometimes a term like a hidden layer is used, to describe that. That's just nomenclature, not that important. It's just something in the middle, and there could be many things in the middle. And then at the end, there's an output layer. The output layer is very important, as you'll see, because that's where there's feedback that's gotten as you start to train your network. That's where the neural network starts to know that, what do I need to do next so that I can get smarter as a network to do what I've been designed to do. All right. And the names of the connections, right, between these things. So this looks like something you can see, feel, and touch, this neural network. But that's exclusive. That's really just a representation, right? We can't actually touch this thing, but they are really just a series of mathematical operations. What you feed in is data, and one of the important things about all of this is that to do compute, you have to convert things to numbers. So the input layer is really just data. For example, in my field, my space, I work in computer vision. I know today's session and module, this afternoon session is all about computer vision, right? So an image, a video are just a series of numbers, right? It's just, intensity, RGB, and also the location. On the XY plane, what is a function of a function of two-dimensional space, and it's 1 to 3 depending on if it's a black and white image or if it's tricolor, or you can even have more. But the fundamental thing to remember about that is that everything is numbers. If it's a self-driving car, everything is kind of like a movie, but that's also just an additional dimension where you have a static image, and then you have another one and another one and another one and another one. And we might all have seen illustrations and animations of early animations of Disney with Mickey Mouse, with the ears, and then it's moving, and somebody's actually literally sketching these out, and you layer them on each other, and that's how you get a movie, right? So exact same mathematics comes into play with just an additional dimension in this case, which is time. So you have these static images, and with time, you get multiple different types of images that you're able to see. And so that data comes in, and then you will do something to that data. And these are mathematical operations, and they're these things called weights, which will be trained, meaning that they can change their learnable parameters. You will modify them, change them, and then you get something on the other side, and that's a score. We're all familiar with the idea of a score. You're getting graded for something. So this network, when it starts out, is going to get a grade. Is it a good grade or a bad grade? If it's a bad grade, so here's the score, right? If it's a bad grade, that means it got the wrong answer. It's going to be penalized. It will serve punishment, right? And that's why this is in red and there's a minus sign. And it comes back in here, understanding that I don't want to serve that punishment. I did something wrong. How can I learn? This is where the deep learning comes into play. How can I change the numbers? Remember, these, even though we represent these with lines and arrows, they're really just mathematical operations. We're going to get into that in this class and see exactly what all that means, how that squares out. And then if it gets the answer right, on the other hand, it gets a reward. And this just continues over and over and over and over and over until our neural network becomes learned. It has learned what it's supposed to learn, and now it can diagnose the disease without ever having seen it before, right? All right, so let's look at that. So this is a very important picture. This picture here is a very important picture because it tells you the whole process, the idea of learning, the idea of feeding in data. At the end, like for example, you give it this one. This is a person's retina that has a disease. It goes in, and what goes in? We know that these are just numbers, like I said, right? So this is like a 0, that's a 1. This is a 0. This is a 1. This is a 10. That type of thing. And there's sort of just an array, a matrix of numbers. Those go in. I've represented those as these beads. And then we do some math to that. We're going to go through that math in this class and convert these gradually into another set of numbers. And since this has a disease, we at the end put a teacher, a supervisor, supervised learning. We're going to then give supervision so that our teacher will then know what and whether this thing was correct or not. If it was not, it gets zapped, punishment. And it comes back in here, and then it says, something bad happened, I did something wrong. How can I learn from that particular experience and do it differently towards getting the right answer? On the other hand, if it gets it right, the supervisor at the end, which is, we're going to see later on, I'm going to use a term called the loss function, but hold on to that thought for now. We're just going to call it the teacher right now, the supervisor. Supervisor gets the grade, the score on the other end, grades it, says, you got it right. So the neural network remembers I got it right, so I did it well, or I almost got it right. So let me even keep going in that direction, keep getting smarter in that direction. And when you run this over and over and over with your NVIDIA GPU on AWS, Google Cloud, or Azure, or whatever other thing you're using, or your own setup in your brand, you do that over and over, bam, you end up with a network, because there are going to be numbers here that are constant numbers, fixed, such that when you take those numbers, now you know the sequence of operations, and you hand it a picture that it's never seen, didn't see it during training or not. You just give it that picture, which is, remember, a set of numbers, and run it through that thing. It'll come out, and what it's going to spit out will be the right answer. And that's how the neural networks work for all the different types of applications. I wish I could take questions at this point to if anyone had any, but I'm not sure that I can do that. And if I can, please do let me know, either chat, or you guys can WhatsApp me, and we can the admin can, and we can make that happen. Otherwise, I'll try to finish early, and then we can go into questions and see, because I really want us to walk away with the key elements of how neural networks work. I know we've already used neural networks. This is about looking at how it actually functions. All right. So these are just a couple of pictures that I got from blogs, and just giving you a quick overview of what we're about to get into now. So I talked about data. Everything is data. I talked about how movies are data. I talked about how when you're driving, when somebody's driving in a Tesla, autonomous driving, self-driving, everything in their environment that they're taking in through LiDAR or camera are actually numbers. Whenever somebody has a retinal picture, it's all numbers. So that's the input data. So that's these X1 through XN. That's the convention that we use to denote these. And then those weights, which are sometimes you'll see the term trainable parameters, right? They're going to be changing based on the score, based on what the supervisor says. This is supervised learning. Then we're going to take those, combine meaning multiply, add, and then sum them up, called a linear combination. And then you put it through a certain function. Like you've heard the term sigmoid. We're going to go in a little bit into that. You've heard the term ReLU, rectified linear unit. You've heard the term tanh, etc. Those are just examples of activation functions. And you can have an activation function that's actually just linear. It just scales it by a fixed number. And that number could be 1, meaning you just do nothing to it. All of those are valid options. And then you get the output. The output is then compared to the true answer, or so-called ground truth, to then, the supervisor then works off of that. So that's the idea. That's the general gist. And so there are these terms that we're going to be diving further into, like neural network anatomy, structure, input data, these X's over here, nodes, weights, activations, and loss. Now, what is this? Well, is there anyone in here who might be wondering whether this picture is intimidating? That, how did we get to this point looking at, this thing that looks like a transformer, or some kind of, whether it's spaghetti or some mesh, can be intimidating, perhaps, not for everyone. But maybe for someone, at least in the room. So I want to assure you that we're going to dissect this, in the course of this lecture, and hopefully get on the same page. So we'll see eye to eye in terms of exactly what does this mean. All right. Neural network physiology. Physiology is function. How do things work? Anatomy is structure. Remember I said earlier that I'm a physician, so I'm mapping it back to that. How the human body works. We look at things like structure. You have arms, bones, legs, joints, and that type of thing. And then you have sort of like the life force, the energy, the thing that makes it tick, how do the cells function, and all that type of stuff. When you look at a neural network from that perspective, you can say the structure is made up of input data, which are called nodes. The middle layers we also use the term nodes, and then the connectors, which are trainable, are the weights. And then there are these activations. The activations are important because they allow your neural network to learn typically in a higher dimensional space. So they allow more flexibility for the neural network to understand the different types of features and what they mean and come up with a representation that can effectively perform well in the field when you generalize. Now that's a lot of words to say that it gives you more room, more leverage, okay? Because if you're just a linear thing, you can't really get around the corners. But if you're now doing sigmoids and things like that, then it allows you to do this. That's number one. Number two is that we will see that in trying to understand the way these neural networks work, we are going to talk about calculus, which is important, and not all of calculus, but particularly this idea of the rate of change. How is something changing? And that's because learning is about changing, right? If I start out and I don't know something, and I want to get to a state in which I know that thing, I have to change, right? And the scientific, objective, mathematical framework by which we measure change and how quickly it occurs is exactly called the derivative. That's sort of one of the basic building blocks of calculus. So it also becomes important, these activation functions, because they are differentiable. They can work with the calculus. They don't get stuck, because we're then able to actually study these things. So those are the two roles that activation functions play. And then the loss function, as I mentioned earlier, is essentially the loss function coupled with the ground truth. Those two things together are the teacher. They are the supervisor. They're the person assigning a grade and as you come back and forth. But more specifically, the loss function is something that you wanted to get to be as low as possible. It's exactly a measure of how badly is the neural network performing. And that's why we use the term loss. How badly is this neural network losing the game? And so you want your loss function to drop to as low as it possibly can. All right. So now we have here a neural network. So the best way to understand things is to break them down into their parts. And it's always best to isolate things out and start with the simplest case and use a particular example, make it concrete, have particular numbers. I was in the room with you all, and I had a blackboard or chalkboard, and we could actually, put some numbers to this and do some workshop. I mean, we've typically done this course in like a 4-hour session, but so we might not be able to get into the depth, but it's going to be a great homework assignment for you all at the end. So let's look at this example. It's still a little bit abstract in the sense that I'm using variables, I'm using numbers x1, I'm using representations x1, x2, x3, w1, w2, w3, as opposed to numbers, 5, 72, 12, and 14, and so on. But you can fill in the blanks afterwards. So this is an example of a neural network. So let's say x1 and x2 and x3 they represent, a picture, right? And you have that picture, and you want to learn something about, the representations that picture encodes. These connections here are the weights, as I said. The mathematical operation, so-called linear combination that you will do to this thing is as follows, right? For x1 is connected to, both output nodes, h1 and h2, via weights w11, w21. Notice the convention that we're using here is that the source, where the thing is actually going to, is the first number. So this x1 is being connected to h2. It's going to h2, so we're using 2 here. Those are bookkeeping things that you kind of have to track so that all the math would work out, right? It's not inherently it doesn't inherently convey physical insight. It's not telling you, it's not helping, it's not necessary to understand the essence of a neural network, but in the representation of how these things are built, that's what we're getting into now with this. I just want to point out the difference between those things, right? Okay, so here, you'll take x1, multiply that by w11, and you'll get this part out here, h1, and sigma of h1 is that. And then you'll multiply x1 by w21, right? And you'll get that. And then you'll multiply x2 by here, by w12 and by w22. This is called matrix multiplication. And so basically you'll have x1 times w11, x2 times w12, x3 times w13. Add all that together, you'll get h1, and then you'll apply sigma to that. And then you'll do the same thing for the second row. x1 times w21, x2 times w22, x3 times w23, you'll get h2 and you'll get that. Okay, so let's look at that again. As I said earlier, this representation is important. It's important because, from a computational standpoint, matrix multiplication is fundamental. It's an easy way to represent things so you can see them. And it also does convey some physical insight inside of it. And it's also very important for speeding up computes, right? So, but what you do need to understand is not necessarily this matrix representation of it, but more so, what did we just do and why? All right, so what we just did is just this, right? We said x1 times w11, that's x1 times w11, x2 times w12, x3 times w13. This representation here, the way I've written this down here, is the exact same thing as the top one. And so this is what matters. Then you get h1, and then you apply sigma. Sigma is the activation function. We're going to look into that. Things like, sigmoid functions like ReLUs, like tan H's and the like. And then for the second row, you do the exact same thing, and you get that out. So that's how we go from the input thing, our image or data or word vector, right? This could be a word or whatever it is that you're trying to do your deep learning on, or it could be some kind of numerics, fintech, like dollars or input, outputs, profits, losses, whatever the case it is that somebody is trying to apply AI to. And then this is a network that just adds a second layer to it. And this tells you what happens when you have a second layer of output, right? So, so in the second part, it's the exact same thing. The only difference is that the input now is the output from the previous layer. And you'll do the exact same math, meaning that now these are the outputs, right? So these outputs are H2, H1, 2 to the 2. This notation tells you it's the second layer. So this is the second H1, and this is the second H2, or H1 of the second layer and H2 of the second layer. And the inputs now are not X1, X2, X3, because we're talking about just this part. The inputs are the outputs of the previous layer, which are sigma H1 of 1 and sigma H2 of 1. And then we do the exact same thing. We do a matrix vector multiply, and that gives us, and then we apply sigma, and then we get the second output layer. And that goes on forever, depending on the length of your neural network, depending on the shape of your neural network. Now we've seen it all. And you can apply that to any neural network, regardless of what it looks like or what you're doing there. Okay, great. So, and this just shows you what this looks like from an arbitrary perspective. Arbitrary meaning that it's not necessarily X1, X2, X3. It could be anywhere inside of that chain, and you can just go ahead then and apply it. So the fundamental structure and this is not specific, again, to neural networks. This is really just basic linear algebra, which is important if one was interested in doing research in deep learning. Absolutely important and necessary. But for the purposes of this lecture, actually, the matrix vector representation is not necessarily essential. What was essential is that you know what these operations are, that we're taking the weight, multiplying it by the input, and the other one based on the architecture, that there's a mapping there, and then you can apply the activation to it. But this tells you how the shape of the so-called weight matrix relates to the structure of the neural network. Okay, so there's a certain layer. So you have a certain number of nodes feeding in. Those are the input nodes. Remember, we had the input vector, like in this case, and then it has to be multiplied in that way. So the breadth of the weight matrix is the dimension of the input layer, and the length is the dimension of the output layer. Because when you multiply this, that tells you the number of outputs that will come out of that. And this is a good example where you can see how that relates. This is something that is I would have loved to ask if anybody recognizes this architecture and what it is. Let me see if does anybody know? Let me see if I can get back to the chat and see if I can browse. Okay. Yes, I'm sure a lot of you recognize this. And this is a variational autoencoder. It's sort of just got that V shape where you take the input layer and you basically boil it down, you condense it down, right? So there's effectively compression that has happened, information compression. So there's some stuff that was in there that you didn't need to have in there that was not.
Yeah, were you able to access the chat? Because we have someone who answered your question.
Let me see. I was not, but I think it's. Let me see if I can.
So we have a few comments.
Probably because I'm slideshow, because I'm right.
Okay.
Okay, let me see if I can do that because it would be nice. Let me see what I can.
Okay. Okay.
I think because I'm sharing my screen, maybe okay. I don't have the option. Maybe.
Oh, okay.
Let's see.
I should just read it out to you, if that's fine. So we have some. It's a multi-class classification. That this particular image, he referred to it as a multi-class classification.
I see.
Then another person, Asamak, has said it's a neural network with hidden layers. Yeah, so those are the answers to your questions, to your question.
Good.
The image.
Yeah, and both of those are good, and neither of them are wrong, which is great. Awesome. And that also shows you it shows you just the versatility, of neural networks, because indeed, once somebody could build a V-shaped or any type of shaped classification model, and that would absolutely work, for multi-class classification. And then the other, someone else said it was what was the other one?
A neural network with hidden layers. That's what he referred it to.
Right, and that's also true, absolutely, because it has more than one layer, more than two layers, not just an input and an output. And so that middle layer is absolutely be called a hidden layer. Absolutely. So great. So that just shows you a lot of the versatility of what this does and what it looks like. Let me go back to full screen. Slideshow. Okay. Yes. Yeah. Wonderful.
Quickly inform you, as in we have about 15 minutes to go for your session. We really appreciate it. Thank you very much, sir. Yeah.
15 minutes. Thank you for the reminder. Yeah, we'll get through it. We're on track, actually. Okay, great. So the activation functions, as I mentioned, have an important role, and the primary role of these activation functions is adding expressivity, to a neural network. And so let's go over these, quickly. This is probably the most important one, the most widely used one. These two, anyway. But the sigmoid has, certainly has special importance. If you look at the equation here, 1/1 plus e to the minus z, what happens when z is 0? I'll tell you all, and you can see that, as well. When z is 0, e to the minus 0, anything to the 0 is 1. So you're at 1/1 plus 1, you're at a half. So you're here. What about when z is very large and negative, or like minus infinity? You have a hugely large and positive number here, plus 1. This denominator is infinity. The whole thing is 0, so that flattens out. What about when this number gets super big? E to the minus large number is 0. So 1 plus 0 over 1, that goes to 1. So it shows you the shape of this. And here's a ReLU function, and then here's here's the sigma we just talked about, and then this is a tanh, which the tanh behaves very similarly, and the equation looks similar to this. It has a 2 here and then a -1, and that's how you get this shape. So these are the sigma that you use in the setup, and this is a whole list of activation functions, and you can design your own activation function and custom implement that in Keras, quite easily in Python or in PyTorch. Back to this picture from earlier, which is our loss function picture. Again, the loss function is telling you how off you are. So you want the loss function to you don't want to have a lot of loss, right, in the thing. So if your loss is big, it means that something went wrong. And so if your loss is a large number, that means that you're going to get penalized. If your loss is small, it means you got the answer right largely, and you would be rewarded for that. Now, this is probably if not the most important slide, it's one of two, right? The back propagation slide is probably, maybe number 1, and this would be number 2 then. And this just kind of shows you what the loss functions would look like. So example of very simple loss functions. Say y is the ground truth, and this is what comes out of your neural network. If you look at the difference and take the absolute value, the more different these two things are, the larger the loss. So that's a loss function. And the closer you are to the right answer, the lower the loss. And if you're exactly at the right answer, the loss would be 0. So this would work well as a loss function. This is another case where you'll square it and you'll get a similar type of effect. So those are sort of the effects that you get. For other loss functions, you have here categorical cross entropy. I'm sure you guys have heard that term, but sometimes that term is confusing and intimidating. So here you have a categorical cross entropy loss function. It's the exact same thing as binary cross entropy when the number of classes in your classification is 2. So this equation here, probably everybody in the room is familiar with this sign, which is just a plus sign. And so when C is 2, you just have 2 terms in this sum, and you can expand it out and it'll look just like this. Now, why is this categorical cross entropy a loss function? Why does it work? Just take a moment and look at it. This TI here is the ground truth, right? And in a certain scheme that we call one-hot encoding, the TIs are either 0 or 1. So there's only 2 things they can be, nothing else. And the TIs, when you sum across all the I's for a given output, they must always add up to 1 in this encoding. And I'm going to show you a picture on the next slide. And then here, this final activation function, we know what the activation functions are, when applied to the score at the end, must add up to 1 when you are using a certain activation that's called softmax. And the softmax is basically, if you take raise it to the power of the score, for all the possible outputs, say it's cat, dog, rat, and rabbit, right? You have these 4 different things. Whatever comes out of it, raise each one to the exponent, add all of them up, and then for any particular one, you're just taking a ratio. So this ratio is always going to be less than 1, and added across all those numbers is always going to equal 1. So that's a softmax. And the power of that is it basically gives you a probability of that output. So you might be saying things like, well, it's 30%, cat, 70% dog. Or it might say 50% cat, 50% dog. Or it might say 0% cat, 1% dog. So it's always going to be guessing and giving you a so-called softmax. So when you have that, you can have any type of output score, but this one is prominent and you'll see it often because it has that property. All right. So back to this top part, where this is the ground truth and it can only be 0 or 1, in a binary classification problem, that looks like this. If the correct answer is 1, right, you can see what will happen to the loss function. If the correct answer is 1, it means that the wrong answer is 0. And that's because the two things must add up to 1, right? So this part's going to disappear. And so that tells you what has to happen to the score. What does the score have to look like if the right answer is 1? What does that do for the loss? And here you can see that the log of x, as x increases, right? This is the shape of log x, right? And minus log x goes the other way. So here you have log of a number. And if that number is 1, log of 1 is what? 0. So that means that if the correct answer is 1, we know this part disappears because this one must be 0. And if your output, your probability says 1, it means this whole thing is 0. Your whole loss will be 0 if you get the right answer. What happens if you got the wrong answer? Wrong answer means if instead you said that when the right answer is 1, let's say you said it's 0. Well, what's log of 0? As you approach 0, your log goes to minus infinity. Huge negative number. So minus 1 times minus infinity is plus infinity. Your loss blows up. So that's why cross entropy works and binary cross entropy works. And it does so in a one-hot encoding system, whereby basically for each output, you essentially have a 0 or a 1. So all this is 1, all of these are 0, it adds up to 1. All of these are 0, this is 1, it adds up to 1, and so on and so forth. And that's why we had that. That's how we write that over there, okay? Now, gradient descent. Stochastic gradient descent. That's critical to neural networks and why they work. And this is where we're going to talk about a little bit of calculus. I know we have probably about, we should have about 20 minutes left if it's an hour long. But let's try to finish all of this in 5 minutes and then have at least 5 minutes for questions. So stochastic gradient descent. So the idea of functions is very critical. So when you look at the loss landscape, this is loss. You're actually walking blind and you don't know exactly where you're going. The whole process of training an algorithm is you want to drop the loss to the bottom as low as you can, where this blue part. How do you do that when you don't know what happens in what direction? Well, the way you do that is using calculus. And where you're here, if you're over here, there's a slope. The slope tells you what direction to go in. If you go too far, you might end up in the wrong place. That's called your learning rate. This idea of stochastic gradient descent is the notion that, and again, this is a computational convenience expediency, is the idea that you can't actually get the right answer without using all the data at once. If you have to use all the data at once, you can't afford it, right? There's too much compute that would be required. So it was quite groundbreaking to find out that if you have 1 million retina pictures, you can actually just take them 32 at a time. And based on those 32 alone, what the loss tells you, what direction the loss tells you to go in, go that direction, and take the next 32, go that direction, take the next 32. And of course, the bigger your batch size, the smoother your approach, so to speak. And the smaller your batch size, the more stochastic, the more zigzag. Sometimes you actually go the wrong direction, like diffusion, but ultimately you get to the right place. That's the idea of stochastic and gradient descent. And so here you have these weights, and in the calculus of weights, right, you're looking at using your information that you have, what you have learned, to do updates, weight updates. So if where this is the weight, and the weight, as we know, is a function of the loss, we've seen that. We've seen that you combine input values using a linear combination to get the next thing and so on until you get all the way to the end. And so when you get to the loss, you have a large function that's a function of the weights. And this formula tells you how to update the weights. I'll give a quick example. Say you're here and the rate of change of loss with respect to weight is what? Positive. You see, slope is positive, rise over run. This is a positive number, right? What that means is if you want to come to the bottom, you must move back. You can't move forward. How do you do that? Well, this formula tells you you're going to then take this positive number multiplied by a small positive number, the learning rate. This gives you a negative number. That means you decrease your weight. What if you were here and you had a negative rate of change? The rate of change, the slope, which is this part, rate of change of loss with respect to weight was negative number. So you're subtracting a negative number, which means you're adding a number. So that tells you if you're here, negative slope says move forward, increase your weight in your next iteration WK plus 1. That's critical. That's the whole idea of the weight update. And that is the whole formula for the learning. And so we'll see that again. Now the chain rule. Chain rule is critical. The chain rule, the rate of change of loss with respect to the weight of something is the LDW if you have a function L of sigma of W. This is a neural network, right? We just saw sigma, we saw W's. When you have this, calculus tells you, chain rule tells you that the rate of change of L with respect to this inner variable W is the rate of change of sigma with respect to W times the rate of change of L with respect to W. You keep going out that way. Your neural network gets larger like this, W, sigma, beta, gamma, and you can do the exact same thing to get the rate of change of loss with respect to any given weight in that network. And so you'll have here the LDW is the alpha dW times the alpha dW times d beta, the alpha times the gamma, the beta. And you can just look, if you cross this out, you're going to end up with the only two things that are not crossed out. Guess what? The LDW. So that's chain rule. Chain rule plays a key role in back propagation. Now, I said the binary cross entropy slide was probably the second most important slide. This slide and its friend are the most important slides here, which is back prop, because this is the whole thing, in terms of how you actually learn in an algorithm from a training perspective. By my count, we've got 15 minutes, so I should be done in 5, and then hopefully we'll have 5 more for questions, right? So this shows you everything, right? So here we are. We looked at a neural network. We said it's a linear combination of input nodes, x1 times w1 plus x2 times w2, and then you apply sigma, and then you get the output. Let's call that output f. And I've written what it means here. F itself is not a weight. That's why I've written the formula here. F is exactly when you got the first layer, the previous layer, and you did your linear combination, you applied your activation, whatever that comes out to, that's your F, right? Okay. So when you go forward in the learning, that's called a forward pass. Computationally, you know that to learn on the way back, you have to change the weights in a way that will decrease the loss. And I've shown that weight update formula. To do that computationally, it's expedient, it makes sense, it is smart to store certain gradients so that you can use them by leveraging the chain rule on your way back. Let's take a look. So x1, x2, you multiply x1 by w1, x2 by w2, add them together, apply sigma. That's this f. You get this f. While you've just done that, before you carry on in the forward pass, you already know you're going to be coming back, applying chain rule to know how to do weight updates. So it's time to store the information you're going to need on the way back. And so you'll then take that output, f, and it's a function of w1 and w2. So you'll then take the rate of change of f with respect to w1 and w2. They're called local gradients, store them in that node, and carry on with your journey. Because guess what? On the way back, after you determine your loss, and you start to unravel that loss, right, by changing all the weights along the way, you would want to know, how do I update W1 and W2? We know how to do that, right, with our weight update formula. And that requires the rate of change of the loss with respect to W1 and W2. To compute each of those things, we need these local gradients that we stored before. And so every step back propagates using information from the step that's right ahead of it. And that's how the whole thing works. We've seen that just now for what basically is a one-layer network. It's a great example because when you get to the end, and you have your loss, you also have your truth value, the ground truth. The loss is a function of the ground truth and the immediate layer, the final output layer. So you can work this out on your own with an example that then applies the weight update formula at every step. The weight update formula requires the rate of change of the loss with respect to that weight. You know how to compute that now using the chain rule. And so for a one-layer network, you can program this in Python on your own, come up with the most simple example, like 12, 13, 5, 500, or something like that, 17, actual numbers, and then code up the actual neural network in a for loop that will ensure that you fully understand what backpropagation is and what each step is inside of your network. And, we're at the end, and we've covered a lot, in this short time. That's so fundamental. And so as you go out, I just want to encourage you that, to understand that, data science has a broad landscape. And it involves, everything from engineering, like web technology development, to actual research where you're trying to improve the state of the art on the algorithms, and then to the enterprise. How do you leverage data science for corporations or for companies for ensuring that you can get products and services to customers that are improved and that are better. So use the internet, use Stack Overflow, YouTube, all the free resources that are out there. And the most important thing is just to keep persevering and improving your skill set. Thank you so much. This has really been a joy and a pleasure. We've made good time. It looks like it's 9:04 my end. And so we have technically 11 minutes. I know you guys should have a break in between. I don't know if we have time for questions. I'll turn it over to your admin at this point.
All right. Thank you very much, Doctor, for that enlightening session. I believe we have participants who are truly, truly appreciative of the session. Thank you very much for the insights that you just shared. So